two-dimensional motion. So we'll look at vectors. We've talked about vectors, but we'll look at how we add vectors. Many of you have done the lab already, so that's what we're going to be doing in this chapter, is adding vectors and looking at how we deal with vectors, finding the components of vectors. And then we'll begin to apply that in the end of this chapter and into the next chapter, and the next chapter, and the next chapter, and the next chapter too. So what we do here, we're going to use a lot, both in this chapter and upcoming chapters, including next semester. Morning, Ashley. All right, so some of this we've seen already. Vectors have magnitude and direction. You know, that means they have an amount. Say if you have a displacement vector, it's a certain distance, so many meters, and it has a direction, some angle with respect to the axis. Scalar quantities have magnitude only. You know, we talked about vector and scalar quantities. Some vector quantities include displacement, velocity, acceleration. We'll also see forces are a vector quantity. Scalar quantities, on the other hand, include things like distance, speed. Oh, shoot. They've been having trouble with it. We might have to go with the whiteboard. I'm sorry. I know that if you can't see very well the whiteboard, we might just have to move up, okay? Let me give it just a second. They've been having trouble with it. Yeah, let's just do that. Sorry about that. We have a bulb part. It just needs to be replaced. They've just been sort of waiting for it to get replaced. I have fuzz on my face. I felt like something fell down on me. No? All right, so so our scalar quantities, which have magnitude only, that includes things like speed, distance, time, mass. We talked about those in a previous chapter. Tamara, can you see this okay? Yeah? All right, if you can't see, please let me know. Mariah, can see okay? Awesome. We're going to represent a vector graphically like this. We'll represent it as an arrow in a certain direction. So this is how we represent it graphically. And there are going to be two things about this. We'll have a distance or a length. The length of the vector gives the magnitude. And then we'll also have the direction of the vector. So the direction of the vector is going to be some angle. So this represents the direction. We've seen this before already, actually, where we have a length of the vector and then the direction. Usually the direction is going to be measured from the x-axis like this, but we see some differences in that. If we have a bigger vector, that just means it has a bigger magnitude. So for example, right here, I have this long vector. It has a certain magnitude. And then if I draw a similar vector like that, this vector has a smaller magnitude. All right, so let's say if this is x, then this is going to be 2 times x, or excuse me, 1/2 of x. I'm going to draw my vectors with an arrow over them like that. So we usually draw our vectors with an arrow. So for example, my acceleration, I'll usually draw it with an arrow over the top. My velocity with an arrow over the top like that. Though you'll see that I'll sort of grow lazy in that, because as we'll begin to deal with vectors a lot, and I'll just sort of drop that at some point. Another thing about vectors is we can move them around however we want. So if I have a vector like this, I can take it and I can translate it anywhere within a coordinate system. So let's say that this sits inside a coordinate system like this. I can take that vector, as long as I keep its magnitude and its direction, I can take that vector and move it around however I want. So I can move it there, I can move it there, there. I can move it however I want. these vectors are going to be the same. Right, let's do the geometric method of vectors, of adding vectors. We're going to consider two vectors, A and B. This is called the tail to tip method. And on your test, you'll have some multiple choice questions about the tail to tip method. I might also ask you when I have you do adding vectors numerically, I might ask you to sketch them out too by this tail to tip method. So let's say that I have a vector A, and that vector A has a magnitude and a direction that looks like that. So it has a certain length, it's in a certain direction. And then I have a vector B. Let's say that B is like this. So it's in a different direction, it has a different magnitude. If I want to add these two vectors, let's say that I want to know what is A plus B, then I can do it like this. I draw the vector A, and then I draw the vector B. I draw B so that the tail of B goes to the tip of A. That's why it's called the tail to tip method, because the tail of B goes to the tip of A. And then the resultant, A plus B, this is going to be A, this is going to be B. The resultant, A plus B, will look like this. I like to think of this as a like a displacement, where if I start here, I can walk along this way, and then I can walk along this way. That is the vector A and then the vector B. But that's exactly the same as if I start here and I walk along the vector A plus B. A common mistake that students make is they'll take the vector A and they'll draw it like this, and then they'll take the vector B and they'll draw it like that. But that's not the tail to tip method. And then they draw A plus B, something like that. That is not correct, okay? Another common mistake that students make is that they'll draw it correctly at first. They'll do A and B like that, but then they draw the vector there in that direction. That's not correct either. In fact, if this is A and this is B, what do you think this is? Okay, yeah, we could call it C. But how is this vector related to A plus B? Want to give it a gander? No a priori reason for you to know this, but I think that you might be able to reason it out. If I switch the direction by 180 degrees of this vector, how is it then related to these two vectors? Anybody want to give a gander? Hmm? Oh, that's a good guess, but that's not correct. But yeah, it's going to be negative A plus B quantity. So negative A minus B. It's just the negative of that original vector. Okay? Um, so if I negate a vector, if I negate a vector, so let's say that I have A and I have B, and I want to know what is A minus B. Well, if I make the vector B negative, as I've done here, I'm going to flip its direction. And so just take a moment and write out A minus B on your page. I think I'm following the notes here. Am I following it okay? Are y'all able to fill in the notes with this? No. Okay. Well, beginning on page 68, the length of the arrow gives the magnitude, while the direction of the arrow, that's the direction of the vector. So the length of the arrow gives the magnitude. And then where it says the smaller vector in this figure, I drew this earlier, but if I have two vectors like this, the smaller vector, yeah, Catherine? The length of the arrow gives the magnitude, while the direction of the arrow is the direction of the vector. The direction is the direction. You with me? Okay. I'm sorry for this. It's not real convenient to know. All right. And then here, the smaller vector here has the same direction. It's the same direction, but half the magnitude of the larger one. All right, so we said if this is x, this is going to be half x. It has half the magnitude of the larger one. And then, as I said, we can draw vectors the same as long as we keep them in the same coordinate system. So this vector is the same as this vector is the same as this vector. As long as I keep them in the same direction and with the same magnitude, I can move them around however I want. As long as you don't change their magnitude or their direction. That's on page 69. As long as you don't change their magnitude or their direction, then you can move vectors however you want. You can translate them. And then we have the tail to tip method. And you have that space on 69, and that's just this, that when I have two vectors that I want to add, I can add them up in this way. So on page 70, you can place the vectors, you can find the sum by placing the vectors tail to tip. And then if you are subtracting vectors on page 70, if you're subtracting vectors, you simply switch the direction. If you're subtracting vectors like we did a minus b, where was it? Right here, I've already erased it. But if you're subtracting vectors, you switch the direction of b. You can also do this for more than two vectors. If y'all did it in lab for three vectors, I can draw that. Where, gosh, how was it? You had a vector that went like this, I think, and then a vector that went like this, and then you had a third vector that went like this. And so you can do this for three vectors, A, B, and C, and then the sum is going to be beginning at the tail of the first one, at the beginning, and then drawing it down here. So this is going to be A plus B plus C. So you can apply this to more than two vectors. Those of you in engineering that are pre-engineering, you have a whole class on this. When you take statics, you're going to spend a chapter or more just on vectors. You'll probably do the graphical method again, and then you'll also do the numerical method. In fact, the whole darn class is like nothing but vectors. We'll get into that a little bit in a later chapter where we actually do some statics problems. We'll get into it a little bit in chapter 4, but then later in the semester we'll do it again. Okay? Let's do a little quiz. Is this going to work for me? My clickers will work, but I won't be able to show you the responses. So let's say that I have two vectors. Can I see what y'all have, Asia? Yeah, so on page 71, where you have two vectors, that's fine. I can look it up. Thank you. A, B, that are magnitudes 12 and 8. What are the maximum and minimum values then? Is it 14, 22, 3, and 96? Lazarus, can you look on with Asia? So I've opened up the clicker base. You can go ahead and click in. If A is equal to 12 and B is equal to 8, A equals 12, that's the magnitude of A, and B is equal to 8, which of these is a possible solution for the vector A plus B? If the magnitude of A is equal to 12 and the magnitude of B is equal to 8, which of those is a possible solution for the sum of A plus B? And in particular, we're looking for the magnitude of this because there's no directions given. A is equal to 12 and B is equal to 8, the magnitudes of those vectors, which of these is a possible solution for A plus B? In your book it says about minimum and maximum values, which you will need to consider that to come up with the right answer. But which of these is a possible solution for A plus B? All right. Think about the orientations of A and B. The orientation of A and B that'll give you the maximum value, and the orientation that'll give you the minimum value for A and B. And then that'll help you pick out the right answer here. There is only one right answer. All right, I'll stop at 135. 135. Okay, about half of you put A and about half of you put B. Actually, slightly more of you put B. Uh, it is A. The answer is A. Because if I have 12, the vector A right here is 12 units long. The vector B is right here. This orientation gives us the maximum value of A plus B. And A plus B then, by the tip to tail method, this is the tip to tail, right? I'm drawing from here over to here. It's going to have a value equal to 20 because 12 plus 8, this one's 12, this one's 8. There's no way for you to get 22. But you say, but what if they're at an angle to one another? Well, let's try drawing them at an angle to one another. So there's A and there's B. This distance is actually some amount less than this distance. You can imagine this as this comes down, that this vector gets bigger in length. Okay, so you can never exceed 20. What is the minimum for the sum of A and B? Or what orientation would they have to give us the minimum? It's going to be 4 because I'll have 12 in this direction and then 8 in this direction. And then the sum, A plus B, is going to look like this. And it's going to have a magnitude equal to 4 because 12 minus 8 equals 4. Where did I get the negative 12? Let me step back for just a second. What I have here are magnitudes only. These don't have any directions associated with them. It's just the magnitude. So the vector A could be in this direction, it could be in this direction, or it could be anywhere in between. It could be pointing in any direction at all. I just give you the magnitude. In a similar way for B, it can be pointing in any direction at all. So what I want to ask myself in this question is, what is the orientation that gives me a maximum value for the sum of A plus B? And the orientation that gives me the maximum value is when they're pointing in the same direction. When they're pointing in the same direction, they're going to add up to equal the maximum value of 20, the magnitudes of them. And you can't have anything bigger than 20. You can't add those vectors in any way and get anything bigger than 20. And then the minimum value is going to be oriented like this, where one is in the opposite direction of the other. And this is like doing a difference, A minus B. In this case, my minimum value is 4. You can't get any value less than 4 when you add these two vectors. Okay? Well, you might say, well, gosh, maybe here I could get a minimum value. But if you imagine, this is 12, this is 8. As I close this angle, make it smaller and smaller, eventually, I just get to this situation. All right, so those are the limits on how we add our vectors. Our maximum is going to be 20, and our minimum is going to be 4. Is me okay on that? Yeah? Nicole? Okay. All right. Let's see. So the answer there was A, right? Yes, Emma. Oh, it's just the only one that's in between 20 and 4. Right? Because all these other answers are not between, they're either smaller than 4 or they're bigger than 20. So A is the only one. So that orientation A is going to look something like this. It'll be, 12 in this direction, and see, would it be? Yeah, it's going to be an obtuse angle, I think. Yeah, so it'll look like this. So it'll be A, B. I don't know what this angle is, but something bigger than 90 degrees. 14. I think that's right. I'm not entirely sure. But some angle that's not 0 and not 180. Yeah, wanna? No. I mean, we will, but not in this case because it's not a right triangle. Okay, you can only use that for right triangles. But we're going to get to that. Okay? Let's try this other quick test. It's in your book, but I'll draw it up here too. I'm going to go ahead and start the clicker. It's on page 71, the one with the arrows. I've already started the clicker, but let me draw the problem for you up here. You'll see something like this on the test too. You have to do it in the lab as well. Consider that I have a vector A, looks like this. B looks like this. I want to know what is A minus B. And then I give you a series of vectors. A looks like this. B is to the side. C is up. And D is to the side. So this was A, B, C, and D. If I sum these two vectors in this way, which is really a difference, adding A to the negative of B, which of these represents the correct answer? It's on, so go ahead and put in your answer. Okay, what do you have to do to B in order to do this sum? What, Heather? Right, you have to change the direction. That's right. So because it's negated, so you have to change it by 180 degrees. All right, I'll stop in 5 seconds. 5 seconds. Just go ahead and guess if you're not certain. 2 more seconds. Okay, looks like about 18 of you put D, and that's the most that you've had. So I draw A. A looks like this. I draw it first, and then I draw B, or rather, this is negative B. I have A, and then negative B, and then I draw the vector A minus B. All right, so that's going to be D right here. If you draw it the wrong way, like this would not be correct. Drawing it this way, you would have put B, and quite a few of you put B. But this isn't correct because you're starting at the end and drawing to the beginning. You always want to start at the beginning. Start at the beginning and draw to the end. Most of you actually, or not most of you, but the second most popular answer was A. And how would you get A? You just add B, right? So you draw A first, and then you don't negate B. So if I do A, and then I do positive B, that would give you, actually that would give you C. It would look like this. So y'all might have done this way. This is not correct. This would be the correct answer for A plus B. And then to get option C, the right answer would be, well, it would be minus A minus B. It would be the opposite of this. It would be minus A, which would be like that, and then minus B, minus A, minus B, and then this would be the sum, minus A minus B. Okay? You with me, folks? Yeah. Right here? Well, right here, we're adding the vectors because they're in the same direction. Like we would say that magnitude of A, actually, we're adding them because they point in the same direction, but also we put them this way because it gives us our maximum value for the sum of the vectors. Oh no, that's not a negative. Right here? Sorry, that was left over. Is that what you're confusing you? Yeah, that's not a negative. It's just 12. Okay? All right. Y'all clear on this too? Graphical addition? Again, you have a multiple choice question, and then you'll also probably within the test you'll have a numerical addition of vectors, and I'll probably ask you to draw the vectors graphically as well. Not do it to scale like you did in lab with a protractor and the ruler and all that business, but to sketch them out properly. Okay. It will help you to be able to sketch vectors properly when we get into chapter 4, because we'll deal with systems that have 4, 5, 6 different force vectors in them, and it'll give you a good idea of what the answer is supposed to be if you can sketch out the vectors properly. Okay, we're going to skip that other quick test question because it's just like the one that we did before. But the answer for that one, the one on page 72 at the top, well, you tell me, what is it supposed to be? It is supposed to be C. It should be 32. It's just like the one that we did over here. You find the maximum. The maximum of those two vectors is 37. The minimum is 13. And so it's between 13 and 37. Now let's look at the components of a vector. I'm going to try turning the projector on. Sometimes it'll come back on. Components are projections of a vector onto the x or y axis. So if I have a vector like this, the vector A, I draw it on my x and y axes. The x component is just like this vector projected down onto the x-axis. So we'll call this AX. We don't usually put a vector, an arrow over this because this isn't really a vector. It really only has a magnitude. The direction is given by the subscript. So the direction means that it's in the x direction. And then the y component of this vector looks like this. That's my AY. It should come up a little bit more. I always like to think of shining a flashlight on my vector. If I shine a flashlight over here, the vector is going to cast a shadow onto the y-axis. That will be the projection of that vector onto the y-axis. Then further, we can move our vectors around. I think this is on your next page. But if I move those vectors around, this is my vector A. I can move that vector y over here. So this is AY, and this is AX. And that should look familiar to you, right? That's a right triangle. The AX and the AY are always going to form a right triangle because of they're on the X and Y axes, which are perpendicular to one another. So they'll always form a right triangle. And that's why our trigonometry is so important, that we understand our SOHCAHTOA and we understand our Pythagorean theorem. Because this angle is theta, and because our SOHCAHTOA, we can develop expressions for our AX and AY. And you want to do more than memorize these. Like you're going to use these a lot in the coming chapters, so you just want to know these. Like you want to, when your heart beats, it beats for the X and Y components of your vectors, that you know them just immediately. So if I say that the cosine of theta, that's adjacent over hypotenuse, in this case that's going to be AX over A, the magnitude of A. And so I can solve this for AX is going to be A cosine theta. And then in a similar way, I can say sine of theta, that's opposite over hypotenuse, is going to be AY over A. So I can solve that for AY, and that's A sine of theta. So those are our expressions for our x and y components. If it helps you memorize them, always remember that I have x and then I have y. That's alphabetical, right? Y comes after x, C, and S. S comes after C. If that helps you, if not, just go back to your original definitions. We're going to use them so much that you'll begin to be familiar with them. But it's one of those things you might want to put on a little postcard or whatever and tape it to your kitchen cabinet or to your bathroom mirror or whatever, wherever you see it, that you can remember these things. This always assumes, by the way, and we'll see that this will cause a little hiccup later, but this always assumes that my angle is measured from the x-axis. Because if I measured my angle from another axis, say right up here, then it would change them because it changes what is the adjacent and what is the opposite side. We don't need to sweat that too much right now. For now, we'll just stick with this. And when we get into chapter 4, we'll see a little hiccup. All right, we can also find the angle. If I know AX and AY, I know the angle then is the inverse tan of, what is it, opposite over adjacent. So what is it? AY, right, over AX. All right, if that's not familiar, don't sweat it. We're going to get into it a lot. You'll get a lot of practice with it. In some cases, not until we get to chapter 4, but in some cases you might need to rotate the coordinate system. It's on page 74. Rotate the coordinate system to make a problem easier. We'll see this with the inclined plane. You might need to rotate the coordinate system just to make the problem a little easier. So let's say that I have two vectors. I have one vector that is over here, and then I have another vector that is over here. When we get into this, we'll see that these vectors are kind of hard to deal with when they're off an axis. So since you can choose your coordinate system in any way, then we can choose our coordinate system, say, to line up like that, so that we can rotate our coordinate systems so that the axis actually falls onto the vector. No need to sweat that right now. We'll see it again with the inclined plane in chapter 4, where we'll actually rotate it, and I think it'll make more sense then. So let's not worry about the theta and the phi stuff that's written there, the angle. Okay, so now to add vectors. This is going to be our numerical way of adding vectors. If we take two vectors, A and B, and we want to add them so that their sum is R, we want to know what is the sum of these two vectors. We're going to say that R is equal to A plus B. We also need to recognize that R is the sum of its components. That is that R is equal to Rx plus Ry. It's equal to the vector sum of the x components of R and Y. Because if I draw R, it's going to look like this, Rx and Ry. So what we need to do is we need to figure out what are the x and y components of R. And we can do that by considering the x and y components of A and the x and y components of B. So the components of R are going to be the sum of the components of A and B. And I'll draw a picture for this, but let me first just write that out. This is still on page 74. Rx is going to equal to the sum AX plus BX, and Ry is going to equal to the sum AY plus BY. Let me show you in a picture. I think it'll be more clear. Let's say that I have my two vectors, A and B. And then we'll do an example. But let's say I have my vectors A and B. I'm going to first draw my coordinate system. Let's say that this is the vector A, and then we'll draw the vector B at a shallower angle like that. So this is my vector A, and this is my vector B. I can draw my x component for A right here. This is AX. And I can draw my x component for B right here. This is BX. It's just the shadow of that vector onto the x or y axis. Likewise, I can draw the y component of A. This is AY. And then the y component of B. This is BY. Right, but notice that I can also draw my vector R starting here and going all the way up there. This is my vector R. But notice that Rx is this component, and Ry is this component. Okay, so graphically we can see that Rx is the sum AX plus BX. Y'all follow me on this? Head nod or a no? It's okay too. Yeah, Emma? Well, they don't have to start at the origin. She said, does BX and BY, should they start at the origin? They don't have to start at the origin because I can draw them wherever I want. I could draw them at the origin if I wanted. I could draw BY right here, but I've chosen just to translate it up here. Because it's like I'm shining a flashlight and it catches B and the end of it's over here and the other end is up here. It's the shadow, the Y projection, or the projection onto the Y axis. Okay, but the important thing here is that Rx is equal to the sum of these two vectors, and Ry is the sum of these two vectors. Okay, so if you can find AX and BX, and AY and BY, then you can find these two vectors, and then you can find this vector. All right, so our steps are going to be find the x and y components of the two individual vectors, add those x and y components, and then find the magnitude and direction of the sum, vector r in this case. Let's step through an example. We'll take two vectors and go through those steps together. Probably will have a question like this on the test where I just give you two or three vectors and I ask you to take the sum of them. Yeah. Let's not worry about that right now. It's not going to come up until chapter 4, and I won't say it's complicated, but we'll address it then. Students tend to get a little confused about that. But yeah, if that confuses your whole rotation of the coordinate systems, don't sweat it right now. We'll get to it in chapter 4, and it'll make a lot more sense then. All right, so vector A is 1 meter long. Anytime I have a vector, I need a magnitude and a direction. And it was 45 degrees from the plus x, I think, right? Is that right? Okay. And then vector B is 2 meters long and 60 degrees. And that's also from the positive x. We'll see that our angles can be from any axis at all, but the default is to measure it from the positive x. All right. First thing I want to do is find the x and y components. So AX is going to equal to A cosine theta. That's equal to 1 meter cosine of 45. And that's 0.71, I think. 0.71. AY, in a similar way, is A sine theta. And it's going to be equal to what? I know. If I have an angle at 45 degrees, what kind of triangle does that make? A right triangle, but also a what? It's an equilateral right triangle. You could call it an isosceles, is that what you said? Yeah. But an equilateral right triangle means that both of those sides are the same. So that means that this is also going to be 0.71. I'll go ahead and write it out though. It's 1 meter times sine of 45. These two are equal. And so that's equal to 0.71 meters. And then in a similar way, we can find bx and by. Bx is going to be 2 cosine of 60. By equals 1 sine of 60. Or excuse me, 2 sine of 60. Let's see, this is 1, all right? And this is 1.9, 1.7, 1.7. Right, so those are our x and y components for all of them. Then I want to find out what is Rx and Ry. By the way, if you had a third vector, you just find the x and y components of that. So I add the components. Rx is going to equal to Ax plus Bx. That's equal to 0.71 plus 1. And then Ry is Ay plus By. That's equal to 0.71 plus 1.7. I'll just make this 1.7 and this 2.4. So those are my x and y components of R. And now for our final step, we want to know the magnitude and direction of R. The magnitude of R is the square root of 1.7 plus 2.4 squared, because this is a right triangle, with 1.7, 2.4. So the magnitude is this value. And then if I want to know this angle, I do my inverse tan. So theta, that's my time. Oh, we have 5 minutes. My theta is the inverse tan of, gosh, what is it? I always forget. Tangent is opposite over adjacent. So that's going to be the y over the x, 2.4 over 1.7. Somebody tell me what these values are when you get them. I don't have them written down. Let's call it 55 degrees. And the magnitude was, I know, 2.9. That sounds right. All right, so the magnitude of R is 2.9 meters, and theta is 55 degrees. I would write that as R equals 2.9 meters at 55 degrees above or from the plus x-axis. I think that should be, yeah, that's all on 75. Let me, we can sketch this out. Let me sketch it out. You can do it off to the side there. If I draw vectors A and B, what we've done graphically here is I draw my vector A, it's 45 degrees, 1 meter. And then this one is 2 meters at 60 degrees, so this is my vector A. And then this one's longer. This is my vector B. What I've done is I found AX. AX was equal to 0.71 meters. And then I found BX. BX was equal to 1 meter. It's not necessarily to scale, but you get the idea. AX, BX, and then I find AY and BY. AY was 0.71, BY was 1.7. So I have 0.71, 1.7. Then I add those together, and then I do the vector sum. So vector sums doesn't mean just adding two numbers together, but going through this whole business of the Pythagorean theorem and the tangent function. Right. If I translate this vector over, now that's translate it over, then my vector r is going to start here and go up there. So this is my vector r. So graphically, that's what we've done. We found the x and y components of A, the x and y components of B, and then we find the that gives us the x and y components of R, and then we use those to find the angle and the magnitude of R. Right? Before we go, I just want to point out one other thing. This isn't in your notes, but I just want to point it out. Is it true that I don't have unit vectors in your notes? I didn't see unit vectors in there. Can I see? Sorry. Yeah, let me just, this won't take but just a minute, and then I'll let you go. You can just put it off to the side there. Unit vectors we're going to use particularly in this class, and if any of y'all go on to Calc 3, some of you, I think Kim may just take Calc 3. You'll have a whole set. Calc 3 is vector calculus. So you're going to do a lot of the stuff that we do in here with vectors, where you're adding up vectors, and then you'll do other things like dot product and cross. Is that okay to take that away? Yes, okay. So just off to the side, unit vectors. We're going to use unit vectors to give x, y, and z directions. So we're going to use the unit vector I, the unit vector j, and the unit vector k. And all these tell us are that this is in the x direction, this is in the y direction, and this is in the z direction. I draw my z with a line through it to distinguish it from my 2, so get used to it. That's my z. It has a little line through the middle. All right, so I, j, and k, these have a magnitude equal to 1. So when I write my vectors, they don't affect the magnitude of the vector. So for example, r, I would write like this. I would say r is equal to my x component, which was 1.7, I, plus my y component, which was 2.4, j. We'll use unit vectors a lot. Have y'all seen unit vectors before? They're not that complicated, but they might be new to you. And if they're new to you, they look funny. But I'll use these unit vectors to represent the x and y components of vectors. And it makes dealing with vectors a lot easier. You'll like them in the end. All right, we'll stop there. Y'all have a great Friday. Remember, soccer's at 4. Football's tomorrow at 3. 3?